And now, capacitors in parallel. I'm very excited. Here we go. I should have dressed up. Actually, don't have pants on. Capacitors in parallel. EMF on the battery. Here we go. And just because this is Rice and you guys are special, I'm going to do 3. I mean, look at that. C1, C2, C3. They're not touching. I got them a little too close, but the plates do not touch. What will happen? Well, now we have junctions. So now we should probably use the junction rule. We don't have currents. The junction rule usually applies to a current. So this, I'm going to put this quotes, the junction rule. But remember, where that charge we get on these plates came from is that a current does flow. So we'll say this is the current version of the junction rule. Some total charge flows out of the battery. And if I could draw this as one junction going to 3, but you get the idea. Whatever charge flows in here has to flow out here. So if we say Q1 plus Q2 plus Q3, then whatever came into these junctions has to go out. So the junction rule in this case is that the total charge equals Q1 plus Q2 plus Q3. Maybe you get how that works by now. Charge has to be conserved, so it has to go somewhere. And on this side, the same thing happens. You get your negative Q coming out, negative Q total, negative Q1, negative Q2, negative Q3. All right, so we have that. And basically we can just substitute in what Q is equal to, right? It's equal to the capacitance of each one times the potential difference across each one. So let's just do that real quick. So we know the battery is just looking for some equivalent capacitance, right? So the Q total, according to the battery, is the equivalent capacitance times the EMF. Same formula we used for series. That's all the battery knows. So we can use that for Q total, C equivalent times the EMF. What about Q1? Well, Q1 must be C1 times delta V1. What is delta V1? What is the voltage drop across 1? It's got to be the EMF. See the way these things are hooked up? The same potential is here, is here, is here, is here, is here, is here. And if this is, we're calling 0 volts, 0, 0, 0, 0, 0, 0, 0, 0, 0. It's also at the EMF potential difference once everything calms down. What about C2? Also at EMF. C2 at EMF plus C3 also at EMF. EMFs go away. And we have that the equivalent capacitance of this parallel arrangement is just C1 plus C2 plus C3. And if there were more, it'd be like that. So again, it's kind of the opposite of resistors. For resistors, if they're in parallel, you have the inverses. But for capacitors, if they're parallel, you just add the capacitances. And if you want to see if you can make a little physical sense out of that, because I know you love to do that, and I love to see how does this make more sense, is when you add things like this, the value gets bigger. When you add the inverses like before, the value gets smaller, but here the value gets bigger. And look at these, the way I drew them. It looks like a bigger capacitor. If we had a bunch of individual capacitors and just hooked their plates together like this, it makes a capacitor with a big plate. And a capacitor with a big plate, the capacitance has to go up. So if you forget these formulas and somehow you've lost your equation sheet on the exam or something, you could sort of reason it out that way. That looks like a bigger capacitor, doesn't it? Whereas the series capacitor had to divide up its potential drop. That's why its capacitance goes down, is it can't put all the potential on everything. They have to divide it up. That's the reason. Oh my God, I have a whole board on capacitors and resistors have opposite behaviors. Okay, I'm not going to record that one, I'm just telling you. I've said it multiple times. Capacitors and resistors have opposite behaviors. When resistors are in series, the resistances add because the potential difference is proportional to the resistance. The capacitances add as inverses. Why? Because the charge, or the potential for the capacitors goes as 1 over C. The delta V equals IR, where R is on the opposite side from delta V for resistors, it's on the same side as delta V for capacitors. That's why they fundamentally act differently. Oh, we're done.